actually wanted to say something about this because it may look like a completely obvious statement. It's actually close to a completely obvious statement, but it's not the same thing. The left and right are not the same, right? But this thing on the left is the additive inverse. Additive inverse of A. That is that which one adds to A to reach the additive identity. Right? So we have this thing, the additive identity, right? That's the zero matrix. And then there's this thing called the additive inverse. Additive inverse, the thing that you add to A to get to the additive identity. Okay. And on the right-hand side, what we have is the scalar, right? Scalar multiple of A by -1. Right. So this is actually a valid statement. It's not just saying A equals A. Right? It's not a complete tautology. It's not a complete tautology, but it's actually saying it says that the additive inverse can be obtained by taking A and then multiplying, scaling it by -1. So. Okay. So let's go on from there. I'm afraid it's not. It won't be too exciting today, but it will get better. It's not. Today is not completely boring. Okay. So here are some non-standard conventions of the author. Non-standard but useful conventions of this text. So first, column vectors are denoted by boldface. Boldface, lowercase letters. Lowercase letters. So on the board, I will double some part of the. I'll double some part of the lowercase letter. Okay, this is what's called blackboard bold. Okay. 2 row vectors are denoted by the same thing but with an arrow above. So lowercase bolded letters with arrows above them. 3, if you have a matrix Aij and it is A11, A12, A1n down to AM1, AM2, AMN. If we write if we write a bolded lowercase ai, what that means is the ith row. So that will be AI1, AI1, AI2, AIN. In other words, the ith row. Okay. And just AI, or AJ, without the arrow above, is going to denote the jth column. So A1J, A2J, down to AMJ, the jth column. Okay, just the notation of this text. Okay, so if A is, for example, 3, 2, 5, -1, A4, and I write A2 with a bar over it, well, I mean the second row. Okay. I mean -1, A4. If I write A2 with no bar above it, then I mean the second column. Then I mean the second column. That's a very loud opening and closing.
sorry.
Okay, so this is, it's non-standard notation, but it's pretty useful. It would be useful when we write something like this. So for mark, we will abbreviate A as either A1, A2, AN, right? So if I'm writing this, I'm expressing A as its column vectors, right? Its column vectors. Or I can express A as like this, A1 bar, A2 bar, AM bar. It's real vectors. So like I said, this is a sort of trivial matter, but it will come in quite handy. Okay, so for those of you who came in late, just some notation, right? Column vectors are bold lowercase. Row vectors are bold lowercase with arrows. If you have a matrix, then the lowercase letter with a number on it indicates the columns. The lowercase letter with a number and an arrow indicates the row. Okay, so back to what we were talking about, algebraic operations, and the most important one will be matrix multiplication. Matrix multiplication. And you could divide it in a few different ways. There turns out to be a best way to do it. It's a little bit complicated, but here's how you define it. So the best way to define matrix multiplication is as follows. So suppose you have a matrix A. So given a matrix A, which we'll denote by aik, as I ranges from 1 to m, and k ranges from 1 to n. So this is an m by n matrix. I'll write it out. And m by n matrix. Okay. And suppose you have another matrix, B, Bkj, where k ranges from 1 to n, and j ranges from 1 to s. So this is an n by s matrix. An n by s matrix. Then we define AB to be the m by s matrix, Cij, where Cij, the ijth entry, is ai row dot bj column. So remember what these things are, right? This is the ith row of A, right? That's to say AI1, AI2, AIN. and we're going to dot that against the jth column of B, B1J, B2J, Bnj. Right? We're going to use the dot, our knowledge of, we're going to use the dot product. So what you get is, of course, summation Aik Bkj as k ranges from 1 to n. Right? You get this sum. Okay, let me put up an example. So -3, 2, 4, 1, 0, 4. Make sure that you understand this, okay? Because we will use this sort of notation shortly. So So just again, the ijth entry of the product is going to be the ith row of A dotted against the jth column of B. Right? That is the ith row of A dotted against the jth column of B, right? Which is this thing, right? The sum as k ranges from 1 to n of Aik times Bkj, right? Because we get Ai1 B1J plus Ai2 B2J plus Ain Bnj, which is the same thing as this, just using the summation notation. Okay, so back to the example. Suppose we have this matrix, and we want to multiply it by 1, 1, 2, 2, -1, 0, 0, 1, 0. Okay. So you say, okay, well, I've got a 2 by 3 matrix and I've got a 3 by 3 matrix. So this is going to end up being a 2 by 3 matrix, right? It's going to end up being a 2 by 3 matrix. Right? The number of columns in the first one has to agree with the number of rows in the second one, because we're going to be taking the dot product of the rows against the columns. And you say, okay, how do I find the 1, 1, right? This is C1, 1. How do I find the 1, 1 entry? I'm going to take the first row and dot it against the first column here, right? I get -3 plus 4, right? So I get 1. Right. How do I find the C1, 2 entry? I'm going to take the first row against the second column, right? So I get -3 -2, so that's -5 plus 4, so that's -5. Keep on going, -6, 1, something 2. Let's just work out what this one is. Take 1 second, 5 seconds, 10 seconds, and work out this one.
5.
5. Because you're looking at the 2, 2 entry, so you're going to take the second row against the second column. So that's fine. Yeah, yeah, that's fine. Okay. Observe. Let's make one small observation that if we look at the matrix, maybe 3, 2, 4, 1, 0, 4, and against the first row, first column, excuse me, we're going to get 1, 1. Right? If we take this thing against the second row, second column, excuse me, -1, 1, we get -1, 5, etc. Right? So that is, you know, if I apply this just to the first column, I'm going to get the first column of the product. Right? I apply this to the second column, I get the second column of the product, et cetera, et cetera. Right? So the observation is this, right? So observe this continuation of the observation. AB actually could be expressed as A times the first column, A times the second column, A times the S column. That is, left multiplication by a matrix can be done column-wise. Okay, now let's write it in English. Left multiplication by a matrix occurs column-wise. Okay. And in my notes, I have this phrase, in general, blah. Okay. I am going to warn you that mathematicians use the phrase in general in a way that's opposite to common language. So normally when you say, you're talking in English, you say, in general, black cats are harmless, right? You mean that in general black cats are harmless, but occasionally they might be a bad cat, a bad black cat, right? That's what you mean in English, right? But when I say in general blah, I mean that in all cases, right? In the general case, right? So here's a specific example, and then in the general case, this is what happens. In general, it really means in the general case, in the general case. So watch out. I tend to use this expression in the mathematics way, and most mathematicians do too. It doesn't mean that this is usually true, but there are some exceptions. It means it's always true. Okay, so yeah, so multiplication, left multiplication by some matrix occurs column-wise. Also notice that if we reverse the order, right? 1, 1, 1, 2, 2, negative 1, 0, 0, 1, 0, negative 3, 2, 4, 1, 0, 4. Then what do we get? What do we get? Right. Here we have one matrix times another, and let's take them in the opposite direction. What happens?
Can't do it.
It doesn't make sense, yeah, right? Because you want to take then the rows of this guy against the vectors, dotted against the vectors of that guy, but they're the wrong size, right? Here we had a 2 by 3 against a 3 by 3. That was great, right? Because this number, the number of rows agrees with the number of columns, right? But here the number of rows disagrees, right? Here we've got a 3 by 3 against a 2 by 3. The number of rows disagrees with the number of columns, right? And so you can't multiply. So matrix multiplication is non-commutative. Doesn't make sense. Multiplication is not commutative. Okay, and even if you have two vectors and you can commute them, so suppose I have like a 3 by 3 and a 3 by 3, well, you can commute them, right? You can, in that case, you can switch the order, but you're not guaranteed the same answer. Okay, so even if the A makes sense, there's no guarantee that it equals AB. Okay, so but should say that this observation about logical multiplication we'll refer to it over and over. So it's a trivial observation, but turns out to be somehow really useful. Okay, back to linear systems. So recall, suppose we have an n by n system, right? So it looks like a11x1 plus a12x2 plus a1n xn equals b1. A blah blah, a m1 xn x1 plus a m2 x2 plus a mn xn equals bm. So you've got a system of m equations and n unknowns. So we can now abbreviate this as follows. Right? Let A be the matrix consisting, the m by n matrix consisting of all the A's, all the aij's. Let X be x1 to xn, excuse me. Let B be the matrix b1 through bm. So column vector b1 through bm. Then, right, consider AX. Right? What's AX? AX is A11, A12, A1n, A m1, A m2, A mn. Right? I'm going to multiply X by that. So this is an n by n, and this is a n by 1. And so we get an m by 1, an m by 1 matrix. Okay, so what are the entries? What's the first entry? There are m entries here. Right, what's the first one?
A11 times x1.
A11 x1.
A12x2.
Plus A12 x2. Plus A1 x2. Right, all the way down to a m1 x1 plus a m2 x2 plus a mn xn. So that is, for the system to be satisfied, we need AX to be equal to B. Right? We would like, if this thing is equal to B, right? B, remember B is just B1 through Bn. To say that AX equals B is the same thing as saying that the system is satisfied. I'm hoping that you're all bored out of your minds rather than not understanding. But is everyone understanding? Okay. Then you're just bored out of your minds. That's good. That's actually as you should be. Okay. So yeah. So in other words, instead of writing, this as a system, a linear system of equations, we write this as a matrix equation. Okay. Right? System of equations can be said as a matrix equation. Right? Instead of writing that, we write A equals B. We're back in junior high school. Right? Where all the trouble was to solve, AX equals B. Right? To solve this problem, we have to solve what is X. Right? And you might think, just divide by A. Right? But it's not so easy. Like, how do you divide? We've talked about matrix multiplication, but we haven't talked about division. And there's a reason for that. Nina?
I was going to ask, is that where the inverse?
Yes,
Okay.
yes. So later soon we'll talk about something called an inverse. If there is an inverse, right, so if there is something that we can multiply by and get something like the number 1, right, we'd like to divide by A. We're hoping that there's a multiplicative inverse, just like the additive inverses we laughed about at the end of class last time. But there may not be, right? And the trouble with matrices is that for numbers, right? For numbers, there's only one number for which there's no multiplicative inverse, 0, right? We can't divide by 0. Right? There's nothing we can multiply 0 by to get 1, right? But for matrices, it turns out that having it's not so easy to have a multiplicative inverse. Okay. Although in some sense it's very easy. So we'll talk. Okay. Yeah. So in some sense you could think of matrix. Like I said, this is the route we could have taken back in junior high. We turned the corner in a sort of wildly different direction. Okay. So that's just notation, expressing things as matrix equations instead of systems of linear equations. Okay. So another key observation. This is sort of like an alternate viewpoint. Okay. So back here, so let me call this thing star. Okay. So this equality, I'm going to mark with a star. So back in star, we can rewrite this. AX could be written as x1, a11, a21, an1, plus x2, a12, an2, plus xn, a1n, an. If we look at the right-hand side here, right, that's the same thing as what I've written here. If I take x1 and multiply this thing, take x2 and multiply this vector by it, take blah, 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 xn and multiply this vector by it, and I add all that together, this is what I get, right? Because I've got x1 times the first column of A, x2 times the second column of A, et cetera, et cetera. That is to say, I could write it like this: x1 times the first column of A, x2 times the second column of A, xn times the nth column of A. Right. Everyone okay with that observation? Okay. All we're saying is that look at it. If you multiply this by that, multiply this by that, and add them all together, then you get AX. Okay, everyone all right? Okay. So then, thus, the question can we solve ax equals b is the same question as can we find coefficients x1 through xn such that b is x1 times the first column times x2 times the second column plus xn times the nth column. Right, this is really key. Okay, so if you were sleeping before, wake up now. Right. The question of solving this equation, question of solving the system of equations, is the same question as can B be realized as a combination of the columns of A? Can B be recognized as a combination of some combination of the columns of A? Can B be realized as a combination of the columns of A? And let me give you the mathematical terminology. So, given vectors B1 to the n in Rm, any sum of the form C1 B1 plus C2 B2 plus Cn Vn, where the Ci are just numbers, are scalars, is called a linear combination of V1 to Vn. So this is saying, is B a linear recognizable, realizable as a linear combination of the column vectors of A? So just to use the new language, is B realizable as a linear combination of A's column vectors? Another definition. The collection
Sorry, we were talking about whether or not those were J's or semicolons.
those are,
No, but yeah.
this is a semicolon.
Okay. And the one after the C as well.
This is an I.
I.
This is an I. So what I'm saying is that all of these CI, CI is in R for I equals 1. So all of the CIs, all of the, so all these things are numbers. So yeah, so any you have a bunch of vectors, and then you multiply them, you scale them, and then you add them together. That sum is called a linear combination of the vectors. So like if I'm in space, I have two vectors, u and v. I take some multiple of the first guy, I take some multiple of the second guy, I add it together, I get this thing, some multiple of the first guy plus some multiple of the second guy. That guy's a linear combination. That's a linear combination. You see that if if you have two vectors, then the collection of all linear combinations is going to be what? If I have two vectors in space, and I look at all their linear, like all linear combinations, who are those guys? They'll form a plane. Right? They'll be basically, you look at the plane through these two vectors, and they will be all vectors who have terminal points on that plane. So right, I've got these two vectors here, right? U1 and U2. Right? I look at I scale one guy and I add it to a scaling of the second guy. I'm going to get something that lies in. I'm going to get a vector that lies in the plane that passes through these two vectors. That leads to this second definition: the collection of all linear combinations of some vectors v1 through vn is called their span. It's called the span of v1 through vn. Of the span. So that gives us another way of rephrasing the question. Is B realizable as a combination of A's column vectors? We could talk about that in span language. Is B in the span of the column vectors of A? Is B in the span? So all of these are the same statement. Can we solve the linear system of equations? Can we solve AX equals B? System. Can we solve the linear system? Can we solve this matrix system? Can we find coefficients? Blah, blah, blah. These last three are basically automatically the same. Can B be expressed as a combination of as a linear combination of the column vectors? In other words, it's B in the span of the column vectors. Okay. So yeah, I'm afraid we've just said the same thing over and over for the last 10 minutes. Everyone all right? So I hope you're getting the language, right? You've got vectors, you have linear combinations of these vectors. You multiply, scale each one, add them all together, and you get some combination. But the combination could be zeros, right? You could multiply everybody by 0, right? And then you end up with a 0 vector at the end. So the 0 vector is in the span is always in the span, because you can multiply everybody by 0. And then if you look at all the linear combinations, then that thing is called the span. Okay? And there's some geometric interpretation of the span. Okay, so we're taking our original question about systems of linear equations and then changing our viewpoint. So I'm going to put up a theorem that is basically completely obvious. So it's in the book, though. They call it the consistency theorem. So AX equals B is consistent if and only if B is in the span. So I've again written up the same thing one more time. Okay. If you're not if you're not yet asleep, then maybe this will do it for you. Here we go. More on matrix multiplication. Okay, so recall, if A is Aij, B is Bij, and AB is Cij. So just using these things to denote the entries. Then Cij is of course the Aik Bkj as k goes from 1 to n. Where this is a n by n, and this is an n by s, and this is an n by s. So algebraic properties. Sort of are, again, as you, what you might expect. Okay. So, right, you know, A plus B is B plus A. Right. This addition is commutative. Addition is associative. Right? Doesn't matter which two you add first. Now here's the one that you may be wondering about. AB times C is equal to A times B, B times C. Do you think that's true? We just defined our multiplication. Our multiplication, involved the dot products. So does it matter if we take the dot products of these guys first and then take the dot products of those guys against another matrix? Or if we do the latter two first and then take the dot product of A against what we got? Do you think it's going to work? It does work.
Yeah.
It actually does work. So associativity is true. Okay, commutativity is false. Associativity is true. Okay, we will work it out. We will see. We'll actually write down. We'll actually see why it works. Other things which you would hope would be true. A times B plus C. What do you think about that? Is that going to work? What do you hope this will be? You hope it's going to be AB plus AC. What do you think? Is that going to work? You've got a sum, and then you take the dot products afterwards. Right? Or you take the dot products first and then sum them. Will that be the same thing? It will. It will. So distributivity works. Similarly, you could multiply on the other side, AC plus BC. Sort of a dumb one. Constants, if you multiply, doesn't matter when you multiply them. You can multiply the constants first, and then that was sort of stupid. I'll put it up anyway. Okay. So now the demonstrations of these facts, the demonstrations of these laws are not all that interesting, but I'm gonna do them anyway, just as examples of how you do an argument, like the first examples of how one does an argument. So how does one prove these facts? So let's look at the first one, right? Why is it true that you want to show A plus B equals B plus A? Right? So we're going to be very pedantic about it, but we'll do it, okay? So to show equality, we need to show corresponding entries are equal. show that all corresponding entries are equal. Right. Well, the ijth entry of A plus B is Aij plus Bij. Right. The ijth entry of B plus A is Bij plus Aij, which are equal. By commutativity of scalar addition. So if you wanted to give a reason, by commutativity of scalar addition. So you think, like, when you're writing an argument, you say what you're trying to show, and then you think what you need to do to show that. Right? So if we want to show that these guys are equal, to show that two matrices are equal, you have to show that corresponding entries are equal, and then show that the corresponding entries are indeed equal, so they're equal. Okay, so it's not exciting, but just an example of an argument. Let's do number 4, right? The distributivity. Okay, so number 4. We want to show A times B plus C equals AB plus AC. I should say that this WTS is just an abbreviation that I use, and for some reason there are professors who grow incensed if they see it. So I don't know, just use it in this class, or you can try it and see what happens in your other classes, just to see the reaction. There's some professors who are very against notation, so if they see an upside down A, they'll become furious, infuriated. Try. You should make shirts with all these abbreviations. Okay. So we want to show this. So of course that means that we have to show that the corresponding entries are equal. So let's introduce a notation that B denote the left side, left column, just for convenience. So for convenience. D be this, and let E be this. Okay. So let's think. Right. Of course, we want to show. We need to show that Bij equals Eij. Right. Where these guys are the ij entries of the corresponding capital letters. So let's think about it. Dij, what's Dij? Well, from our knowledge of multiplication, it's going to be A's ith row, right? A's ith row, so we think A's ith row against B plus C's jth column, right? B plus C's jth column. So we're going to get B kj plus C kj. Plus k matrix from one there. Okay. Right. Okay. Take a minute and write down what E is. What's E? Eij. Just to make sure you understand notation. Okay, time is running out, so somebody tell me what I write here. What is EIJ? EIJ is going to be the ijth entry of this sum. So what's the ijth entry then? I'm going to have the ijth entry of this guy plus the ijth entry of this guy, right? What's the ijth entry of this guy?
It's AIK, BKJ, running from 1 to n.
Right, so that's for that guy. And then, go on.
The other one's AIK, CKJ,
Yes.
from K.
Right. Right. Everyone got that? So, right, this is going to be ijth entry of this. This is going to be ijth entry of that. You add them together, and lo and behold, they're the same thing, right? So, which are the same? Which are the same? So it is true, right? We do have a distributed law, right? So A B plus C actually does equal AB. Okay. Next time, we'll start off with associativity, which will not be as easy as this, but still not that much. So just one step.